Second part of chapter 15, we're going to continue working with complex numbers, and we're going to start with de Moivre's theorem. De Moivre's theorem says that if we have a complex number in polar form raised to an exponent, we can simply raise the modulus to that power and then multiply the argument by whatever number that was. And this is very useful for us in raising a complex number like this to higher powers. What we can do is we can change this to polar form. I'm going to draw a quick sketch of it. I always like to visualize. The real part is square root 3. The imaginary part is 1. So there's my complex number. I'm looking at that triangle. So the argument, if I call that complex number z, the argument of z is going to be pi over 6. The modulus of z is equal to 2. Pythagorean theorem will find that for us. So this power becomes 2 CIS pi over 6 to the 8th. Now I raised 2 to the 8th, and I'm going to multiply my argument. 2 to the 8th is 256, and now I'm going to change to the long form of this. Cosine 4 pi over 3 plus I sine 4 pi over 3. Now I can actually take the sine and cosine. Cosine of 4 pi over 3 is negative 1/2. Sine of 4 pi over 3 is negative root 3 over 2. And now I can distribute. I get negative 128 minus 128 square root of 3 times I. Multiplying this out as binomials would take a very long time. Changing to polar form and then back again and using de Moivre's theorem in the middle allows us to raise to the 8th power or any other exponent very quickly and efficiently. So now I'm going to use what's called the nth root method for finding zeros. And z to the 4th is equal to 1. Let's find the 4th root of z. What we can do is we can write 1 in polar form, and that would be 1 CIS 0 plus 2 pi times k, where k is an integer. Now, using de Moivre's theorem, actually before I use de Moivre's theorem, z is going to be CIS of 2 pi times k to the 1/4, the 4th root. Now I can use de Moivre's theorem. Multiply the modulus of the complex number by 1/4, or raised to the 1/4 power. 1 to the 1/4 is equal to 1. Multiply the argument. So what I'm left with is z is equal to CIS pi over 2 times k. Now I'm going to look at what happens for different multiples of pi over 2. For k equals 0, we're looking at CIS of 0, which is equal to 1. Cosine of 0 plus I sine 0. K equals 1 we're going to look at CIS of pi over 2. Which is equal to I. K equals 2. CIS of pi, cosine I sine cosine pi plus I sine pi. This is equal to -1. K equals 3. We're looking at cosine 3 pi over 2 I sine 3 pi over 2, and that's equal to -I. And for 4 pi over 2, that's the same as 2 pi, so K equals 4 brings me back to K equals 0, the same thing. And we're going to go through this process again. So the fourth roots of 1 are 1, I, -1, and -I. So this says to find the fourth roots of -4, and hence write z to the fourth plus 4 as a product of two quadratic factors. We start out with z to the fourth equals -4. Well, we can't very well take the fourth root of a negative number, but if we change this into polar form, we can apply de Moivre's theorem. So z to the fourth equals 4, the modulus of -4 plus 0I. Visually on an Argand diagram, 0I would be here, would be on the x-axis, -4 in the real direction would be over here. So the modulus is 4, CIS, and the angle is going to be pi, or plus any coterminal angle. Where K is an integer. So Z will be 4 to the 1/4 CIS pi plus 2 pi K divided by 4. And in a side note here, 4 to the 1/4 is the same thing as 2 squared to the 1/4, which is just the square root of 2. So just a simplified way of writing this. And for different values of K, we're going to end up with the square root of 2 cis pi over 4. That's when K equals 0. Or we could have the square root of 2 cis 3 pi over 4. Or we could have the square root of 2 cis 5 pi over 4. And these are for K equals 1. K equals 2. And finally, we could also have 2 to the 1/2 square root of 2 cis 7 pi over 4. That's for K equals 3. And if we use K equals 4, we're going to be back to something that's coterminal with pi over 4. So we repeat through this cycle. So my values that I get when I expand these four things out are going to be 1 plus I, -1 plus I, -1 minus I, and 1 minus I. I'm just expanding out the long way. CIS pi over 4 is cosine pi over 4, I sine pi over 4. And we're going to get some square root of 2's over 2 canceling, so we get nice complex numbers here. So these are the fourth roots of negative 4. And we can use those to write z to the fourth plus 4 in factored form using quadratic factors. So I'm going to take these onto a fresh page. And we're going to use properties of quadratics. So two of the roots are 1 plus and minus I. For those two roots, the sum of these is going to be 2. Remember, this is negative b over a. The product negative 1 plus I times 1 minus I is also 2 in this case. Remember, that's c over a. So a quadratic that I could write from that is going to be z squared minus 2z plus 2. Now I'm going to take the other two zeros, negative 1 plus or minus I. The sum of those is negative 2, and that's negative b over a. The product, when I multiply these together, is positive 2, that's c over a. So this quadratic factor is z squared plus 2z plus 2. We have now just factored z to the fourth plus 4. The last example, we're going to find the 3 cube roots of unity, and we're going to display them on an Argand diagram. And we're going to show that the roots are these, and when we add them up, we get 0. So what we have, cube roots of unity, what we're solving is something cubed equals 1. We were finding the fourth roots of unity. Well, we already did that a couple examples ago. It's anything to that power equals 1. And in polar form, we have this, where k is an integer. So z is equal to CIS of 2 pi k to the 1/3, which is cis 2 pi over 3 times k. So multiples of 2 pi over 3. When k equals 0, we have cis 0. When k is 1, we have cis 2 pi over 3. When k is 2, we get cis 4 pi over 3. And any farther, we're going to repeat through the cycle. Our roots, expanding this out, are 1, negative 1/2, plus the square root of 3 over 2, and negative 1/2 minus the square root of 3 over 2. So 1, here's w squared would be the same thing as multiplying the angle by 2. On an arcane diagram, what we're looking at is z equals 1, that would be there, negative 1/2 square root of 3 over 2, and negative 1/2 negative root 3 over 2, something like this. And what we should be able to see in graphing these is that these three angles are all going to be the same. And if I add up these three roots, they all add up to 0. So here are some problems that you can try.